So an analogy for this is the Quantum Hotel, a discount resort for electrons, and Mrs. K's chemistry land. This is not my wife, Mrs. K. This is my mom. She also teaches chemistry, and she gave me her slides when I started, which was a lifesaver. But I really like this analogy. So if you think of these orbitals as hotel rooms, we've got different floors. That's the principal shell. Right? So our floor is the principal shell. Each room is a subshell. So for S orbitals, that's one room. For p orbitals, that's 3 rooms. And then each room has one bed. Oh, sorry. P orbitals have, the p rooms have 3 beds. So each orbital is a bed in the same room. And so the s orbitals have, or the s rooms have 1 bed. P rooms have 3 beds. D rooms have 5 beds. And F rooms have 7 beds, and you can fit 2 people per bed. And they have to have opposite spins. So they're sleeping opposite directions on the bed. Hotel rules.
Which one's going to have 2 people?
Each bed can have 2 people. So the S room has 1 bed, so you can fit 2 people in that 1 bed, but they have to be laying down in opposite directions. Yes, and money is energy. So all of the people staying in this hotel are very, very cheap, and so they want to stay in the cheapest rooms possible. So they're not going to buy a more expensive room unless there are only more expensive rooms available. So the cheapest room in the discount hotel is 1S. And so let's do an example for this. Let's do oxygen. So if we're doing the orbital diagram for oxygen, you can think of, I guess, in this analogy, you could think of these as like buses or vans or cars, right, that are carrying the people to the hotel. So oxygen as a van carries 8 people. So you have 8 electrons. And so the first people to get to the check-in desk get the cheapest room. And so we put 2 people in the 1S. And then we still have more people, so we put them into the 2 people into the 2S room. Again, they're cheap. They'd rather share a bed than buy their own room. So that's 4. And now we have 2 people left, and the cheapest room, and they'll share, is the 2P. So when we put them into the 2P room, they're not going to share a bed if they don't have to. They're not going to sleep upside down in the bed if they don't have to. So we can put our last 2 people in here, and they don't need to share a bed, so they don't have to, so they don't. Oh, sorry. I did a really bad job of counting. We have 2 more people. So they're also going to go into this 2P room. And so 3 of them will go into their own beds first, but we have 1 more. And so they'll have to share with somebody. Yeah?
I'm just confused. Why does it like the P levels start at 1, or don't they reset to 1? Why do the P levels start at 2 and then the D level starts at 3?
Because quantum physics. It's, I do not know the specific reason for that. It is just how it is. But the number, so the principal shell number, so 1 corresponds also to the number of possible orbitals, or the number of types of orbitals in that level. So 1 only has 1 shell. 2 has 2 different types of orbitals, S and P. 3 has 3 different types of orbitals. And then 4 has 4. So 4F is the first F orbital. And part of it comes down to also, to use an analogy, is like the packing a suitcase analogy. So it's only when you get to higher energy levels, when that space is already sort of filled, that you need to start packing into smaller, different spaces. Right? If you only have a few things to put in a big suitcase, you just throw them into the middle, and they can just take up the middle of the suitcase. When you start trying to pack more and more stuff into the suitcase, or more electrons around an atom, they have to occupy different spaces. And so those spaces become more complicated to fit into the cracks, like shoving socks or underwear into shoes.
So on all of them, you can have two, right?
In each space, you can have two, yeah.
No matter what.
So p orbitals, there's three. In every orbital, you can have 2 electrons. In the p orbitals, there's 3. P orbitals, there's 3 orbitals.
So each one can have two.
Yes.
Okay.
Yep. Each one of those can have 2. Okay.
We couldn't skip it, huh? We couldn't go to 3s instead of the 2p's.
No.
You have to go follow
The lower energy first. Yeah.
Or can we go by twos, like if we do like 1s2 and 2s2, can we do like 2s3 or do we have to do 2s?
You have to do 2p before you get to, yeah, 2. You have to do 2p before you get to 3s.
So this would be something good to pray and kind of have it in our mind, huh? Because this is the way it's going to be.
And I have, yeah, so this is a good one if you know this. There's another way to remember the organization and how to fill these in. That's this guy. And I know this looks really complicated, but it's actually fairly simple when you try to write it out. So this first column is just all of the s orbitals. So you just start at 1s, 2s, 3s, 4s, 5s, 6s, 7s. And then next to that, you start at 2, and you write the 2p orbitals. So 2p, 3p, 4p, 5p, 6p. Right? It's just a column. And then on the next one, it's 3d, 4d, 5d, 6d, always starting 1 down. So you get this staircase. And then it's 4f and 5f. And then the way you fill the orbitals, the order, is by drawing these diagonal lines. So you fill 1s first, then you fill 2s, then you fill 2p. So you follow this in the periodic table, right? 1s, 2s, 2p. And then you'll go to 3s, and then 3p, so on the other side of the periodic table. And then you go to 4s, and then the d orbitals, just because of the way the energy levels work out, we fill 3d after 4s. So then when you start this next diagonal line, it starts with 3d. And then it's 4p, and then 5s. So by drawing the diagonal lines, it tells you what the order of the orbital filling is. And if we go back up to here, you see also that lowest is 1s, 2s, 2p, 3s, 3p, 4s. But then the 4p orbitals are higher energy than the 3d. So we fill those 3d orbitals first. And that's where all the transition metals fill their electrons. So starting with scandium. And then it goes to 4p. More examples are always helpful with these, I feel like. So this is my favorite way for remembering the order of filling these. Yeah.
You have to like print like a blank periodic table and then just write each one in.
Yes. Yeah, so these are easy to practice, and there's actually a periodic table in the book that has the electron configurations for every single element. And those don't change for ground state elements, which is all that we're doing. Those don't change. So you can always fill them in. Oh, of course, here's the periodic table that does that. Now, it's only giving you here the valence electrons, so the highest energy electrons. There are some odd ones. And you can see here that these highest energy are 2s, 3s, 4s. That's the s block. Right? Pink over here is the p block. So their last electrons are in p orbitals. And then in the d block, their last electrons end up in d orbitals. Some weird ones that you might notice on your own. If we go to like chromium, it's 4s1, 3d5. And that's just because when you have the 5d orbitals, it's more energy efficient to have those all filled with parallel spins than it is to have coupled spins in the 4s. So it takes 1 out of 4s, moves it up to 4d. You don't have to worry too much about that. I just wanted to point it out. It's not a typo. It's just a weird effect of electrons. The other one is copper will do that. So it'll be 4s1, 3d10.
How come the ones at the bottom don't have anything?
Oh, are those the
It's an F block.
SG? I think that those are, I'm not sure why they didn't just fill them in, because you could, in theory, fill those in. They might not have existed for very long. I don't know. They've got names here. But those are all of these on the periodic table that are outlined in white, or the white letters with black outline, are man-made elements. So one of the cool things about the periodic table is because of the way that these elements are organized, they predict what the properties of hypothetical elements should be. And a lot of those only exist for just like fractions of a second, fractions of a fraction of a second. And they make them like a couple at a time in large, like the Large Hadron Collider. So you take two heavier particles and you smash them together. And for a brief moment, this new element exists, and then it falls apart because it's not very stable. So that might be why. Good question. I don't know. That's my hypothesis. So yeah, these are easy to practice. They're also a little bit tedious. And so brief summary, though, before we do more of these electron configurations. Lower energy orbitals fill before higher energy orbitals. They can only have 2 electrons each. And they have to have opposite spins when they're paired up. When you have orbitals of identical energy, so like p or d orbitals, they fill one at a time before you pair them up. And then when they are one at a time, they all have the same spin. And so Pauli exclusion principle and Hund's rule. All right, so let's do a few of these here in quick succession, and you'll see what I mean by them being repetitive. So for nitrogen, we'll do the electron configuration first. So where do I start with the electron configuration?
Nitrogen is 7?
Yeah, so nitrogen is going to have 7 total electrons. But we can also use the periodic table to just sort of count through all of the different possible electron configurations. So, right, hydrogen would be 1s1. If we had one more electron, that's 1s2, that's helium. And so we can write down, so okay, we're going to have at least 1s2. And then lithium is 2s1. Beryllium is 2s2. And then in the P block, we can actually use the column, or the, I guess, how many elements into the P block nitrogen is to determine how many electrons will be in the P block, or it will have in the P block. So nitrogen's the 3rd element in the P block, boron, carbon, and then nitrogen. So you can say that this is 2p3. So let's do electron configuration, or the orbital diagram for that. So this will be 1s, 2s, and 2p.
So you can do the 2p3 because 6 electrons can fit on the 2p floor.
Yeah. Yeah. So we'll go 1, 2, 3, 4, 5, 6, 7. Or look at your electron configuration. So there's 2 in the 1s, 2 in the 2s, 3 in the 2p.
So like you wouldn't put the last 3 together because like they don't want to sleep in the same bed if they don't have to, right?
Right, yeah, we wouldn't put these like this
Yeah.
because yes, the analogy, they don't want to sleep in the same bed.
Yeah.
And that one is called Hund's rule. Yeah, so they want to fill by themselves first. Yeah.
Each 2p has 3 spots.
Yes. 2p will have 3 spots, 3p will have 3 spots, 4p. All of the p's have 3 spots.
So then would the 3d's have more spots?
Yeah, so d's have 5.
5 spots.
So they're odd numbers. It's 1, 3, 5, and then 7. So all the s's have 1, All the P's have 3. All the D's have 5.
So because the P has 3, that's why you could put a 3, you can't put a 4 there, right?
We could put a 4. And actually, we'll do oxygen.
So you could 4, 5, 6, you could go
Up to 6.
up to 10 for the P, right? Because you can put opposite. Because 2 people can fit in each bed.
And there's 3 beds
Yes, and the P.
in the P.
But I'm, but
So
you have to
that's-
start with the first 1S, 2S. You know what I mean?
Oh.
Start from the bottom and go up to the top. So you could go up to 10.
Yeah, we'll keep going with these because we're gonna get there. And I think you'll see. So for oxygen then, like I said, every element on the periodic table has the same electron configuration of everything before it, plus 1 more electron. So oxygen's gonna also have 1s2, 2s2, and then it's gonna be 2p, but it's gonna be 4. So 1 more electron. Trying to do these really close together because I'm going to run out of space. So 1s, 2s, 2p. So we're going to have, again, 2 in the 1s, 2 in the 2s, and now 1, 2, 3, 4 in the 2p. And I will say, it doesn't matter where the paired electrons are in the p orbitals. So I always write the first paired one in the first orbital, but it could be the second one. But if you're going to be continuing to fill things up, might as well just keep going left to right. And so save yourself a decision and just do it the same way every time. All right, so that's oxygen. And then for fluorine, actually, I should probably move that down a little. For fluorine, it's going to be all of the same stuff, plus 1 more electron. So it'll be 1s2, 2s2, 2p, 5. And then it'll be a 1s orbital, 2s orbital, 3p orbitals. And then our electrons will go in there. And the only thing that changes is in the p orbitals now. So it's 1, 2, 3, 4, 5. Make sure you're writing these in with opposite spins when they're paired. First one's a half up, second one's a half down.
So then that one looks like you just can go up to neon.
Yep, and so the next one we're going to do is neon.
Yeah.
So 1s2, 2s2, 2p6. So 1s, 2s, 2p, and now all of these orbitals are filled in. And so when all of the orbitals are filled in, that's called an octet. And that's especially stable. So, like I said, electron configurations, if you have to do a whole bunch of them, get a little bit tedious because you're always starting from 1s, and it's always the same thing until you get to the end, and then it changes, if you're going in order at least, a little bit. I think it's still good practice, especially if you're still figuring out how to use the periodic table to do this quickly. All right, so that's our complete filling of the n equals 2 principal shell.
So then this orbital, these would be the dumbbells, huh?
The p's would be the dumbbells, yeah. So, oh, and I'll go find this in a second. Instead of writing all of these out, because you can imagine, right, it takes long enough to do nitrogen, oxygen, fluorine, and neon. Once you get down to xenon, that's 54 electrons. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d10, and you just have to write all of this stuff out. So instead we use shortcuts as the noble gases, right? So the noble gases are especially stable, and we say, okay, if we're going to do something like sodium, we look at where sodium is on the periodic table, right? It's in the third row. So the electron configuration for sodium before that is going to be the same as neon. Let's all write neon in brackets. Say we're starting with this electron configuration, and then we're going to add on to that. Well, what do I add on to that?
You have to do the 3s.
Yeah, 3s, and then it's the first element in 3s. So there's only one electron there. So very, very useful, very, very time-saving. And so on the exam for this, I will give you a question where you have to write out all of it. I'm not going to make you write out xenon and have you go through just 43 electrons for no reason. It'll be something probably in the second row. And then there will be another question where I say, okay, now you can use shortcuts, and then I'll do something farther down the periodic table. Yeah. Oh, so sodium's in the third row. Yeah.
But don't we have like three 2Ps to fill in before we get to 3s?
Well, 3s is first.
Well, that's,
You already did that because you, in the brackets is everything that you've already done for neon. So
yeah.
Okay. This is confusing because it has like on this it has 2P, 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 and not just one.
Oh, I see. Yeah, so for the electron configurations, we sort of shorten that all down to just 2p6 or 2p, and then how many electrons are in there. Let me switch over because when you're doing these shortcuts, though, don't, where is it? Wait, no, it's past that. Don't do this. The electron configuration is argon. Can you read that? It says, yes, the floor here is made of floor. It's like, no duh. So if I say, like, do the electron configure argon, and even if I say use shortcuts, don't use argon as a shortcut, use neon, and then do that road to get to argon. It's not wrong, it's just not very helpful.
So we just have to use the one before, no? Like the chloride.
Yeah, so for any of these, if you're going to do an abbreviation, so like, yeah, if you're going to do chloride, you'd still start with neon as the abbreviation, and then you do 4s2, sorry, not 4s, 3s2, 3p, 5. A lot of numbers. This is for electron, so these are electron configurations. The orbital diagrams are the arrows. And you could do that for, we could do that here too. You could do this for an orbital diagram. So we could say neon, and then we could do, would just be 3s, and then 1. So starting with neon, don't need to do any of that. Those are all full, and just starting here. So this is the electron configuration. This is an orbital diagram. The orbital diagram is not drawing pictures of the different shapes of the orbitals. I've gotten that. When people don't know what to do, they'll just draw the shapes, which is nice. Some people are really good at it. Better than I could do. Okay, so now that we have shortcuts, let's do some of these other ones. So if we wanted the electron configuration for aluminum, where would I start? What shortcut would I use? Neon. So you always start with the noble gas in the row before it. Yeah.
Oh, so you can only go with the noble gases, you can't go with an orbital low orbital.
Yeah.
Oh, okay.
That's kind of because noble gases are special and they represent completely filled. Yeah. So start with neon. There's another reason that we'll get to, which has to do with valence electrons. But so start with neon, and we're starting in the third row. So the first one is 3s, or past, yes, 3s1, but also 3s2, because we're past magnesium also.
So we just count the 2 and 4, we don't count it in the element itself. Like if it's sodium, magnesium, and that's it, just 2?
And then aluminum. So then we'll do aluminum.
Okay.
And so aluminum is the first element in the p block. So that makes it 3p1. Okay. What about for bromine? Uh-huh. Shortcut on argon, and now we're starting at 4. 4s2, 3d, 3d10. The D's are they're one principal shell lower, and the F's are 2 principal shells lower.
So it'll start at, you said it start at 3 and then the F should start at, what is that?
4. The F's start at 4, but they start in row 6. So this is why that staircase thing that I drew is helpful. Actually, here, I'll show you how to draw this out. So it's 1s, 2s, 3s, 4s, 5s. I'm not going to have you go as low as 6, 7, or even 4 or 5s probably. Well, 4s, yes. 5s, maybe. You don't really have to do 5 or 6 or 7. And then in the next column, it's not 3. It's 2, 2p, 3p, 4p, 5p, 6p, 7p. And then it's 3d, 4d, 5d, 6d, 7d. And then it would be 4f, 5f, 6f, 7f. And then you read it on the diagonal. So for bromine, and this is not, sorry, I didn't finish bromine. What would the next orbital be for bromine? 4p. How many electrons in the p? 5. So if the p block is that whole column, so even gallium, indium, and I think that's tellurium, are all still in the p block. So it's all of those to the right of that. So bromine is, starting with gallium, is 1, germanium's 2, arsenic 3, selenium 4. Bromine is the 5th in the p block. So it has 5 electrons in the p orbitals. Yeah?
Only 10 electrons can fit in the D section?
Only 10 in the D because it has 5 orbitals. 5 orbitals that can fit 2 each. So, all right, to illustrate this hack, this trick for doing the orbital and getting this 3D. So for bromine, we would start at 1s if we weren't using the argon, 2s, and then it would be 2p, then 3s, then 3p, then 4s. And so now we're at, that would be 4s. And so when we draw the next diagonal, right, because we ran off the edge here, it starts at 3d. And then it goes to 4p. And so that's why we did this 4s, 3d, 4p. And the next one would be 5s. And then 4d. Does that make sense? I think this is like really take this. This very much is one of those things that I had to do this on my own a little bit to figure out and make sure that things lined up. So when you write this chart thing out for yourself, try to use it, and then when it starts to line up with what the answers are for these, hopefully it'll start to click then. You'll start to see the magic. But let's move on, because we've got to finish off this chapter. For strontium, what would our abbreviation be? What would we start with? KR, which is krypton. KR. And then what would the electron configuration after that be? 5s, 2. Second element, S block. It's in the 5th row. So 5s2. Okay. So these ones, you can really practice them a lot. There's, again, that whole table, this periodic table up here that has all of the elements on there. I would say stick to the first 4 rows. 5 rows if you're really ambitious. Once you get to 6, then you've got f orbitals, and it gets more confusing from there. Let's see, where were we? So we can write out an orbital diagram for argon. And again, we can use abbreviations. So we can start with neon. And then it would be, orbital diagrams. Space this out better. So this is 3s, 3p. And so argon is at the very end of the row. So it's going to have a full 3p, 8 electrons in that row. Total. Sorry, S plus p is 8 electrons. So same thing with the electron configurations, just doing orbital diagrams now. And if it makes it easier, right, you can do an electron configuration first, then do the orbital diagram based on that. So, and this is why we use the noble gases for abbreviations, because what we're usually concerned with, and the thing that determines most of the properties of an element, are its valence electrons. So the valence electrons are just the outermost electrons. They're the ones that when atoms are bumping up next to each other, those are the electrons that are interacting. The rest of the electrons are covered up by those. They're shielded from anything else by those valence electrons. So when we start with, for example, the electron configuration for argon, when we start with neon, we're saying everything neon and before, all of those electrons are buried. And we'll get to this, they're called core electrons. And so then that lets us do an orbital diagram for the electrons that we're interested in, which are the valence electrons, all the highest energy electrons. Oh yeah, it is in here. So those are, all of the other electrons are core electrons. And so actually, let me do the whole, I'm going to do the whole electron configuration for argon real quick. S2, S2, 2p. So that's the whole electron configuration for argon. The way that you can tell what the valence electrons are is they're the ones associated with the highest principal shell number. So the principal shell number is the first number. Right? So that's the 1, the 2, the 3 in front. So from your electron configuration, these ones with the 3, those are the highest. So those are all valence electrons. The rest of these are lower in energy and underneath the valence electrons. So those are core electrons. And this does include the fact that d orbitals are always one level lower. I'll do an example of that. All right, so only the highest principal number are valence electrons. And so we identify them by these, I guess you can think of them as coefficients. And then the number of valence electrons is the superscripts added together. So 2 here plus 6 would give us 8 valence electrons. Just another visual of this. So for silicon, again, these, all of the orbitals starting with 3 are the valence electrons. The rest of them, core electrons. They're on the interior. This is for chlorine. I kind of want to show you, I'm not going to do chlorine, I'm going to do bromine. So for bromine, we're going to do the whole thing without abbreviations. You do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we get 3d10, and 4p5. So that's the whole electron configuration for bromine. Which of these, what are our valence electrons? What was it?
The 3s to 4p.
So highest principal shells only. 4s and 4p, but not the 3d. Because 3 is still still smaller than 4, but it's in the previous principal quantum shell. So our valence electrons are these guys. So those are the valence electrons. All of the rest of the electrons are core electrons. Pick a different color. Okay, so all of these and these 3d10 are core electrons. And I like electron configurations, so you can bet there's going to be a question like this on the exam. Did I make a mistake?
No. How come okay.
I mean, you can ask your question.
So you know how it goes like 1s, 2s, 2p, 3s?
Mm-hmm.
Why doesn't it go 1s, 2s, 3s, and then go to the p's?
Oh, well, it's because we're trying to do things in the energy order that they fill in. So if we go back to like,
Yeah, I was like looking back.
mm-hmm. So
Okay, because it's like this, like the little squiggly line. So it.
yeah, that too, and here just the 1s, 2s, and then it goes 2p is higher than 2s, but it's lower than 3s.
Okay, yeah, because it like puts up.
We get 3s, 3p, yeah. So we kind of like jump back and forth once we get up to higher energies. Yeah, that was a good question. Yeah, so we're going in the order of energy, and sometimes you'll see these two written, I don't generally do this, but with commas in between these. That's fine too if it helps. Helps you see the spaces between them. Okay. So the valence, or the elements in each column, each group, have the same number of valence electrons. So lithium, we can do this one, lithium, sodium, potassium, rubidium, cesium, francium, all have a single valence electron. Beryllium, magnesium, calcium, strontium, barium, radium, all have 2 valence electrons. And then same for all of the elements on the periodic table. Well, ignore the D block for now, because the d orbitals, those are buried underneath. We're not going to talk too much about transition metals. But in the p block now, it's the same as, so boron has 3 valence electrons. These are like the 3a, 4a group numbers that are on the slide here. Carbon has 4 valence electrons. We can count those here in its electron configuration, 5, 6, 7, and 8 valence electrons. And that's why, within a column, elements have very similar properties. And that's why, when I had you memorize the charges that different elements form, they form the same charges. This is what we just said. The number of valence electrons for any main group element is equal to the group number of its column, which are the 1a through 8a. And then the row is the highest principal quantum shell. So we can look at this periodic table again and like see that these are 1 or 2 valence electrons. And that's why these are abbreviated the way they are. It's just the electron configuration of the valence electrons. For the transition elements, they're filling core electrons, and they all have very similar properties because of that. And that's why we also get that -1, row number -1. That's why it starts at 3D instead of 4D. Yep. Trying to get to, okay, so, and this is kind of something I already hit on also, but the electron configuration, if we wanted to do phosphorus, the reason that we start with neon is because that represents all of the core electrons, and most of the properties are determined by valence electrons, so it doesn't matter what the core electrons are for the main group elements. Okay.
So you wouldn't just always start with the element before for a little shortcut?
You start with the noble gas before.
Okay.
Yeah. And so these are sort of the general rules for writing these electron configurations. You represent the inner configuration with the symbol for the previous in noble gas in brackets. And then the outer electrons are determined, the outer electrons, the valence electrons, which is kind of how I've been showing you how to do it already, so I skipped a lot of those slides. The outer electrons are determined from the element's position within its particular block. So if you count like magnesium as the second element in the S block for its row, it's going to have an electron configuration of 3s2, because it's in the third row and it's the second element.
So if we were figuring for phosphorus and we started with neon,
Mm-hmm.
we would go through and configure for like sodium, magnesium, aluminum, right?
Mm-hmm. And you would say that, yeah, it's already got all of those. So like, it's already past the S block, so it has to have 3s2, because that would be magnesium.
So if I was writing it out, I would put neon in the brackets,
Mhm.
and then I would put like how would I
Okay, so
just add on everything that sodium has, or?
so for phosphorus, right, neon in the brackets. Then we say, yeah, so we look at the periodic table, and since those first 2 columns represent the S block, it's past that. So it has to have 3s2.
Oh, okay.
So we would just write 3s2.
Okay.
And then you say phosphorus is the third element in the P block. So it'd be 3p, and then third element means that it's 3p3.
Okay.
Yeah. And then if you do get d electrons or d orbitals, it's one less, its principal shell number is one less than the row number, or the row number minus one. So take a look at some of these. So that's why something like titanium, it's the second element in the D block. So it's 4s2 because it's past 4s1 and 4s2. But then it's second element of the D block, and it's 3d2. All right, so let's do tin. So tin is all the way over here. And so because tin, if we want to do, actually, let me do the electron configuration over here. So tin, we would start from the previous noble gas. Right? So we go backwards, and then upper row, so krypton. And then it's in the fifth row. So we're going to start with 5s2, because we're past the s block. And then there's the whole D block. And the D block's always one principal shell number lower. So if we're in 5d, or if we're in the fifth row, our d orbitals are going to be 4d10, because we're past all of those. And then what's the last part of the configuration? 5p. Yeah, 2. This is the second element in the p block. All right. Any questions? All right, so because the chemical properties of elements are largely determined by the number of valence electrons, everything in a column has very similar properties, especially for main group elements. And the quantum mechanical model explains why hydrogen is so reactive, because we're getting these electron configurations out of the quantum mechanical model. That's what predicted the shapes of the orbitals, and also predicts the energy levels of the orbitals, and that's why we fill them in from the lowest energy to the highest energy. And so it tells us for a lot of elements what their properties are going to be. So atoms with 8 valence electrons, or it's the one exception is helium with 2. They're very, very stable. So none of those gases react with anything. You can force them to, but they don't naturally want to react with anything, because they're happy with the number of electrons that they have. Now that means that everything else on the periodic table that doesn't have 8 valence electrons is reactive and will try to get 8 valence electrons. There's 2 ways of doing that. One is by gaining a small number of electrons, or by losing a small number of electrons. So if we look at the alkali metals, that's group 1A, know those are reactive metals. If you take potassium metal and you throw it in water, it explodes. That's because it's violently reacting with the water, and it's giving up electrons to the water. Because if we look at, let's do potassium. And so potassium, it has, I'm going to start for potassium. I'm going to start with neon here, because I want to illustrate that. So this is going to be 3. Yeah. So I'm doing things a little bit weird here. Actually, let me do it this way. 3s2. So 3s, 3p, and then 4s would be the next one. So this is 1, 2, 3. So this is the electron configuration of potassium after neon. All right, so it wants to get to 8 valence electrons. It wants 8 electrons to be the outward-facing electrons. But it has this one electron that's in the next energy level. So currently, it has 1 valence electron. If it can give up that 1 valence electron, then it has 8 valence electrons that are underneath that. So by losing 1 electron, it reveals a full octet, or a stable electron configuration. And then that makes this potassium plus, because now it has 1 fewer electron than it has protons. So all of the elements in the first group do this. That's why they all have 1 plus charges that they form. And then if you have something in the second column, second group, right, group 2, they all form what charge? 2 plus charges. And that's because if they lose 2 electrons, right, so if we went from potassium 1 over to calcium, that can lose 2 electrons, and then it'll have this same electron configuration, which is a stable electron configuration because it's the same as argon. And so that's why all of those group 2 metals will form 2 plus charges, because it's stable, because they can get to these 8 valence electrons. I should move on, because I think that's the next one. Yeah. So, right, magnesium or calcium or strontium or beryllium, these all lose 2 electrons. Beryllium's case, then it gets to helium, which is 2 valence electrons. But the rest of them want to get to 8. And it would be a lot harder. So let's do the magnesium's regular electron configuration. So starting with neon, right? It only has 1s2. If it wanted to gain electrons to get to 8, that's not 1s, I'm sorry. 3 and then 3p. It would be a lot harder to gain 6 more electrons from somewhere to get all the way up to argon than it would be to lose 2 electrons and go back to neon. Because in general, things don't want to have charges. All right, so these group 2 metals all lose 2 electrons. If we move over to the other side of the periodic table now, we have something like fluorine. So draw out the electron configuration for fluorine. Start with helium. Oh, sorry, let me do I'm not doing electron configuration, orbital diagrams. 2s, 2p, so it's 1, 2, 3, 4, 5, 6, 7. So fluorine has 7 valence electrons normally. If it can gain just 1 more valence electron, that will give it the same electron configuration as neon. And then what charge would it have? Sorry, so if fluorine gains 1 more electron, what would its charge be? Right, so we know that fluorine, chlorine, bromine, iodine, they all form 1 minus charges. And they're forming 1 minus charges because that gives them stable electron configurations. Makes them happy. And if we go farther into the periodic table, we could do oxygen, sulfur, selenium. They all just need 2 more electrons to get up to noble gas electron configurations, and that makes them stable. And then nitrogen and phosphorus do the same. So this quantum mechanical model is the reason why these elements form these charges that I just had you memorize at the beginning. All right, these last slides go pretty quick. So we're going to try and get through these. Or we could just, let's go through a few of them. And we'll still stop at on time. And I won't have to rush because we're going to do more lecture this afternoon. Okay, so now I've talked about these electron configurations. The electron configurations and the number of electrons largely determines the properties, almost entirely determines the properties of different elements. ways that they'll react, right? This is why fluorine would like to react with lithium, because lithium wants to give up an electron, fluorine wants to gain an electron. It's a win-win situation. But the number of electrons also determines a lot of other properties about different elements. And we can just sort of use the periodic table as a guide for these properties. So one of those is atomic size. So the atomic size is the distance from the nucleus. Well, actually, it's the distance between the outermost electrons in the nucleus. And so going from the center to the edge of the last orbital, the farthest away orbital. So as you move across a period, so that's each row is called a period. So we're moving left to right. The atomic size actually decreases. So even though we're adding more electrons, we're also adding more protons. And so adding more electrons doesn't add a whole lot of size because that's mostly going up principal quantum shells. Remember we talked about orbitals. The orbitals get a little bit bigger every time you move down the periodic table and add another shell. They get a little bit bigger, a little bit bigger. If you're moving across, adding just one electron at a time, they don't really get much bigger. But you add more positive charge, more protons to the nucleus. And every time you add a proton, it adds more positive charge. So, and remember, opposite charges attract. So the electrons around the atom are attracted more to the nucleus, and so it shrinks. Then once you go down a row, that's when things get bigger. So size of an orbital depends on the principal quantum number, which doesn't change going across a period. But once you go down, that's when you add another shell. And so going from neon to sodium, it suddenly gets bigger. And then as you go across, it'll shrink again. And you go down a row and it gets bigger. And then as you go across, it shrinks. So atomic size, back to the black one here. Going down a column increases, but going to the right decreases. Yeah, here we go. This is what I was looking for. So it tends to increase as you go down, decreases as you go to the right. And for me, the best way for memorizing these or remembering this was not remembering just like right gets smaller, down gets bigger. It was remembering that cesium is the biggest. So bottom left corner is biggest. Top right corner is the smallest. So then comparing any two things on the periodic table, you say, am I going towards fluorine or helium, or am I going towards cesium? If you're getting closer to cesium, you're getting bigger. If you're getting closer to fluorine, you're getting smaller. Kind of, I don't know if this analogy will land, but I also think of it like, so the periodic table is this flat plane. If the atomic sizes were all the same, no matter where you went, then it would just be flat. But instead, it's tilted. So bigger things, cesium's up in this corner. And then the smaller ones, helium, are in that corner. I guess hold it for that periodic table. Yeah, so it's like this. So the bigger one's over here, and so you're sliding down this way, it's getting smaller. So we can use this, right? Okay, so let's look at a couple of these. You got to remember, too, that going from left to right is a smaller change than going down or up. So if you get some conflicting information there, you got to remember which one is the bigger difference. So if we're looking at lead or polonium, which one is bigger? So lead is here, polonium's here. Which of those is larger? Because which one's closer to cesium? Lead. So lead is the larger atom. All right, so then rubidium or sodium? Because rubidium's closer to cesium. Now tin or bismuth, tin Bismuth. Why bismuth? So which change makes a bigger difference? Principal shell number. So going down or up a row makes a bigger difference because we're removing entire layers of electrons or adding entire layers of electrons to the other side. It's like putting on another coat. Right? So when we go from, if we go from tin and we go to the right one, okay, going to the right one makes it a little tiny bit smaller, but not very much. Going down is like adding an entire jacket on, an entire layer to the outside.
Like Joey on Friends.
Yeah.
Puts on all of Chandler's clothes.
Yes, just like that. So bismuth is bigger. And this is one of those places where it's like, which one's actually closer? But yeah, remembering that the row matters more. And for fluorine or selenium, which one's larger? Selenium, right? Fluorine's one of the smallest. I got time for maybe one more. Ionization energy, we're not going to talk too much about, but ionization energy is the energy required to remove an electron. So how hard is it to take away an electron? And the way to think about this one is how close is something to being, or how close is something to gaining enough electrons to have an octet? So on the right side of the periodic table, fluorine is one electron, needs to gain one electron to get to neon. So if you try to take away an electron from fluorine, that's moving in the opposite direction from where it wants to go. It's going to be really, really hard. And fluorine is actually, I think, the hardest element to remove electrons from. Now, as you get bigger elements, again, we're adding layers between the nucleus and those outer electrons. And so the farther away the electrons get from the nucleus, the easier it is to kind of pluck them off the edge. And so you can also think of that like magnets. Right? I think there's a magnet in this. So magnets, right? If they get even just a little bit away from it, you can't feel the attraction at all. So this is kind of similar. So the farther it gets away, the less attracted it is to the nucleus, the less attractive force there is. On the other hand, if we go over to something like lithium or sodium, they actually want to lose electrons so that they can reveal the 8 electrons that are underneath. So since you're taking away an electron that they don't want anyway, they have really low ionization energies. It's very easy to remove one electron. So this trend is similar then to, or actually it's the opposite. I'm not even going to bother trying to like compare it to atomic size. It's a little bit weird. Because as you move down, outermost electrons are farther away and easier to remove. Oh yeah, okay, so ion is
Like a long distance
like a long distance
relationship.
relationship, exactly. If you find someone closer. So again, you can say, what is the highest? Fluorine is the hardest to remove an electron from. Francium or cesium would be the easiest one to remove an electron from. All right, we'll pick this up this afternoon.